So as we think about fatty acid degradation, which is beta oxidation, and then fatty acid synthesis, which is just fatty acid synthesis, one of the things that's unique about these catabolic and anabolic pathways is they are differentially regulated by location. So to put a couple of notes up on here, again, this location is key. This is the inner mitochondrial membrane. So degradation occurs exclusively, again, that's beta oxidation. Degradation occurs exclusively in the mitochondrion, whereas biosynthesis occurs exclusively in the mitochondrion. In the cytoplasm. So degradation, again, is in the mitochondrion. Biosynthesis is in the cytoplasm. So we have a fairly easy way to sort of regulate what's going on here because we know how impermeable that inner mitochondrial membrane is. So we haven't yet really talked about fatty acid biosynthesis. We've talked about the details of degradation. So this is a great slide then to sort of introduce us to sort of what we're going to talk about with synthesis. So let's review what we know again about beta oxidation, again, the degradative process, catabolic process that's going to break down fatty acids ultimately to acetyl-CoA that will take on to the citric acid cycle. So we've again got that fatty acetyl-CoA. We activated it. We got it into the mitochondrion by that carnitine hat. So let's remind ourselves too, we've got some transporters here. We're going to have carnitine. Okay, carnitine is going to be how we're going to get these fatty acids into the mitochondrion. Once they're in there, they take off their carnitine hat, they put back on their CoA hat, and then we're going to do oxidation, hydration, oxidation, and then cleavage. That's the 4-step mantra I want you to remember. The first oxidation step, again, goes from an alkane to an alkene. So we're going to see the production of FADH2. Okay. Then we have hydration, pretty standard hydration. Hydration of an alkene with water gives an alcohol. And then when we take that alcohol and we oxidize it to a ketone, those redox chemistries, we're generally going to see vitamin B3 that's sort of involved with that versus vitamin B2 when we have FADH2. But at the end of the day, the big picture thing is that we are generating acetyl-CoA. Again, this is the product of beta oxidation, and this is what goes on to the citric acid cycle, right? So that is the details of what we have here. Now, want to make sure to highlight another important piece to think about here is we do not have transporters for acetyl-CoA. So there is no acetyl-CoA transporter. And this is an important sort of fail-safe because that ensures that catabolically derived acetyl-CoA from beta oxidation does not make its way back into the into the cytosol, into the cytoplasm, to allow it to be kind of remade into fats. That would be a futile cycle. This is differential regulation that we didn't see, for example, with glycolysis and gluconeogenesis, right? For the most part, all of the glycolysis and gluconeogenesis steps occurred in the cytosol, right? With the exception of pyruvate carboxylase. But for the most part, we didn't have this separation that allowed us to sort of differentially control and regulate that process. Okay, so I think that's all that I wanted to say here about sort of the degradative piece. We sort of talked about that before. But now what we're going to do is we're going to sort of talk about sort of the biosynthesis sort of piece. So one of the things to sort of highlight is that if we have excess acetyl-CoA, and we should say that this is not excess acetyl-CoA that's derived from fats, because that would sort of be a futile cycle. If we're breaking down fats and then we've got excess acetyl-CoA from fats. This is generally excess acetyl-CoA that's going to be glucose or carbohydrate derived. What we're going to see is we are going to synthesize that into citrate. Okay, so again, excess acetyl-CoA, I'm going to kind of draw an arrow up here. This is going to be synthesized into citrate, and we have a citrate transporter that is going to get citrate out into the cytosol. And then we're going to get it back to have excess acetyl-CoA in the cytosol. So excess acetyl-CoA in the cytosol. Okay, so the key here is, and it should make sense, that we are only going to be doing fat synthesis if we've got an excess of acetyl-CoA. We've sort of talked about that. So we're going to start at the bottom half of this slide because it was degradation, sort of going from fatty acids down to acetyl-CoA on the left. So on the right-hand side, we're now going to have excess acetyl-CoA. So again, excess acetyl-CoA here. That's sort of where we start this process. I'm not going to go through the details now. We're going to have some slides that will talk about this, but here's how this process works. Excess acetyl-CoA is ultimately going to be made into malonyl-CoA, okay? And we're going to see that the enzyme responsible for this is ACC. You guys have heard about that enzyme name from your fundamentals quiz. ACC is acetyl-CoA carboxylase. So that's going to be adding a CO2 group onto malonyl-CoA. Then we're going to have malonyl-CoA and excess acetyl-CoA. The reversal sort of happens here. So we had oxidation, hydration, oxidation, cleavage. Now we're going to have condensation, okay, reduction, and then dehydration. So reduction we're just going to show kind of like that, and then we're going to have dehydration, reduction. So I want you to see the parallels that we have here with the process of beta oxidation versus fat synthesis. So oxidation, hydration, oxidation, cleavage, condensation, reduction, dehydration, reduction. And a big difference here too is we are using NADPH to do this reductive biosynthesis. Remember, we talked about that being synthesized in the pentose phosphate pathway. Purpose of NADPH was largely reductive biosynthesis. Okay, so lots of things sort of in play here that are going to allow us to sort of regulate very closely what's happening here. Your body really tries to avoid futile cycles, so we certainly do not want catabolically derived acetyl-CoA from beta oxidation of fatty acids when we are in a need state to be allowed to go back into the cytosol to participate then in fatty acid synthesis. Okay. So we're going to talk about the details of this process, but this was a nice 30,000 foot view here talking about the differences between degradation and fatty acid biosynthesis.